So I watched JJK some time ago. It's a good anime. It's got lots of cool fight scenes, enjoyable characters, and dope animations. And then there's one thing that stuck out to me. Gojo's ability, the Limitless. It's one of the strongest abilities in the series, but also the most complicated, because it's explained using lots of math terms. Now, being a big ass nerd that I am, obviously I'd be interested. Except, the explanation is kind of bad. Like, to me, the mathematical explanation doesn't make much sense. There's this bit about the convergence of a series, this part I do get, but then there's also this bit about dividing space infinitely. I don't quite get this one. But regardless of the explanation, the effect of the ability makes it look like he's literally bending space-time to his will. Meaning, if I want to explain his ability, I'll need to know about space-time. And so, I took a General Relativity course at my university just to make this video. Okay, not just to make this video, but like, for dramatic effect I said that. For those unaware, in JJK or Jujutsu Kaisen, the power system is called cursed energy. Basically, a Jujutsu sorcerer may accumulate negative emotions, and then use them offensively like mana. Advanced users can also invert this cursed energy and turn it into healing powers, or perform inversions of their cursed technique. The strongest character in the series, my guild Satoru Gojo, has an ability called the Limitless. Upon activation, enemies trying to reach him literally can't. They slow down to a halt as if the space between them and Gojo is growing to infinity. The explanation is applied by a series that behaves like a convergence of an infinite series, that when you add in more and more terms, it gets closer and closer to a certain value, but you need infinite terms to get to that value. Like for example, it might take you 1 second to get closer to Gojo by d over 2, and then it takes 1 second to get even closer by d over 4, then d over 8, then d over 16, ad infinitum. This video, which you might have seen before, does a great job at explaining it. Now, do you know what this effect reminds me of? A black hole. From an outside perspective, when something falls into a black hole, it will be approaching the black hole and slow down right before it crosses the event horizon. From this frame of reference, the object takes an infinite amount of time to get into the black hole, just like with Gojo's ability. And this is why I think Gojo's ability can be explained by the same thing that explains the black hole: differential geometry and Einstein theory of general relativity. Let's go over the basics of differential geometry. I promise I'll make this as comprehensible as I can, so the explanation here is going to be somewhat hand-wavy. If you want more details, I made a paper linked in the description that you can go and read. Okay, so, when you have a curved space, you can still set up a coordinate system that uniquely determines a point. It's like the XYZ coordinates, but curved. If I move slightly along this curved axis, let's call it u and the small change du, and move along the other curved axis v, changing the v coordinates by dv, what's the total displacement that I moved in this curved space? Well, in the simplest case, where the space isn't curved, we can simply use the Pythagorean theorem. But if it is curved, then the answer depends on the curved space that we're working with and the coordinate system that we set up. If the space is curved in a different way, or if the u and v axes are oriented differently, the displacement will be different, even if du and dv remain the same. But all of that information is encoded in what we call the metric tensor. This little guy right here is actually 16 values compacted into one symbol. These two Greek letters, mu and nu, are the indices. In 4-dimensional space, the value of the index can range from 0 to 3. The 0 representing the time axis, and 1, 2, and 3 representing the spatial axis, like x, y, z, or r, theta, and phi. So there can be a total of 16 combinations, and thus there are 16 values compacted into the metric tensor. And this metric tensor answers our question of the displacement in the curved space. Restricting ourselves to 2D, the small displacement here that we wanted, ds, you square it, and it's equal to this formula that uses the metric tensor. So if someone gives you a metric tensor of a curved space, you can use this formula to figure out the distance you move along a path. Let's look at what it means. If we move exclusively along the x-coordinate, then the dy terms are 0, so we only have one term left. The movement along x, squared, multiplied by g11, becomes the actual displacement squared. So G11 here is the square of the scaling factor for the motion along the x-coordinates. The bigger G11 is, the bigger the distance you have to move in curved space, just to change the coordinate x by a small amount. A solid example is in polar coordinates. Instead of expressing the position in x and y, we express it in r and theta. If we move along the theta coordinates, the arc length swept by the movement is r d theta. So clearly, G22, the theta part of the metric tensor, is r squared. Its square root, r, is the scaling factor between the change in the coordinate theta to the distance moved. Can you see how this can be useful in Gojo's case? If the first coordinate is r, the radial distance from Gojo, and we set G11 to be very big near him, it means that when we're close to Gojo, the actual distance in spacetime we need to move gets very big compared to how much we get closer to him. Now take a look at the metric tensor that describes the space around a black hole, called the Schwarzschild metric. This is G00, the time component, G11, the radial component, G22 and G33, the angle-related components, which we'll ignore for now. You can see that indeed G11 blows up to infinity at Rs, the Schwarzschild radius, where the event horizon is. Meaning the distance scaling factor for r blows up, and this plays a part in why it takes an object an infinite amount of time to pass the event horizon. Gojo acts like a black hole in this sense, so let's take inspiration from the Schwarzschild metric to construct our own Gojo metric tensor. Unlike a black hole, Gojo doesn't suck, he's my goat, and if you are far away from him, your motion is unaffected by his ability. So this results in three conditions that the Gojo metric should result in. A. Objects approaching Gojo's event horizon, or the barrier distance, slow down. B. Objects do not get sucked in, unlike a black hole. And C. Trajectories far away from Gojo are relatively unaffected. One metric that might satisfy all three of those conditions is this. Every component is the same as the metric tensor for spherical coordinates, except for the radial component, which is similar to the Schwarzschild metric from the black hole, just squared. Again, we use this because if this value blows up near him, it's like the space-time distance goes to infinity close to him, which should make him unreachable. We have the Gojo metric now. But from this, how do we know how things move around him? From the metric tensor, how do you predict the motion of things? Well, we'll need to use the metric to construct what is known as a geodesic. A geodesic is the shortest path in curved space between 2 points, like a straight line in flat space. Now, in flat space, you can create a straight line by moving with a constant velocity vector. In the same manner, moving in curved space with constant velocity traces out the geodesic. So if no forces are acting on something except for gravity, which in itself is the curvature of spacetime, then its spacetime velocity will remain constant, and therefore it follows the geodesic path. And this is the geodesic equation. The left-hand side represents the rate of change of the velocity vector, and the right-hand side is, well, just 0. What the equation is saying is just that the velocity is constant along the curved spacetime. This hangman-like symbol here is the capital letter gamma. It tells how the basis vectors change as you move along each axis, and is calculated from the metric tensor, like this. Let's throw this equation, along with the Gojo metric, into the math machine, aka my notebook, and let's find out how a particle moves in Gojo's proximity. We'll get 4 equations in total, 1 for the time axis and 3 for the spatial axis. We can simplify these equations further, and let's get rid of phi coordinates for now, so we can run the simulation in 2D. I'm going to assume Gojo is a sphere, and now I plug the equations into my computer and render the simulation. Let's first say that the particle is moving directly towards Gojo. Let's see what happens. Don't forget that this circle I made here is the barrier radius. And it looks like it works. That's exactly what happens when things get close to Gojo. It slows down and then it stops right at the barrier. Alright, let's add in some tangential velocity. I want to know what happens. And why does he suck? He should not be sucking things in. Why is he sucking things in? He should not be sucking things. He should not be sucking in particles. He should suck me instead. Why is he sucking things? What? Okay, let's adjust our metric a little bit. Going back to the equation of motion that we got, when we add in the tangential velocity, theta dot is no longer 0. Meaning this term is no longer 0, which is the reason Gojo's attracting things towards him. This term in the equation stems from the angular part of the metric, so we'll need to change it somehow. I'll do it by multiplying it by some function f of r, and I'll try to find a function so that Gojo won't suck. Using some mathematics, I got the function to be this. If you want to know how I got this abomination, check the paper in the description. But what matters is, this fixes our problem. Still, if you move straight towards him, you're gonna slow down and stop right at the barrier radius. Now, if I run the simulation again with some tangential component, it's gonna be deflected right off, away from him. In fact, by running the simulation, I found a deflection radius around Gojo. If your velocity is not directly towards him, this radius is the closest distance you can get to him before getting deflected away. But if your velocity is perfectly towards him, you can breach the deflection radius but still get stuck at the barrier radius, which acts as Gojo's event horizon. With this ability is the ultimate defensive ability. Nothing can ever breach through it. I'll run a few simulations with varying parameters so you can see it do its thing. Enjoy. Oh yeah, and consider subscribing. Thank you. Apart from that, I also ran one frame of ray tracing to show how it will look in 3D space. As you can see, this is exactly how the anime shows it. Wait. There we go. Okay. Well, now, how does Gojo do it? How does Gojo curve spacetime in a way such that we end up with this metric tensor? Well, I can't answer that since I don't have access to curse energy yet. But from the metric tensor, you can find the Christoffel symbols. From the Christoffel symbols, you can find the Riemann curvature tensor, from which you can find the Ricci tensor and the Ricci scalar, both of which are used to find the Einstein tensor, which is proportional to the stress energy tensor. The stress energy tensor basically tells how energy is distributed in spacetime. Which means, from Gojo's metric that we have, we can find how Gojo's Limitless manipulates the curse energy to be in the configuration that bends spacetime and achieves the effect that we see on screen. In theory, of course, we can figure it out. But in practice, well, the stress energy tensor that I got looks like this. If you happen to have free time to solve it, be my guest. So yeah, thanks for watching to the end of the video. And if you guys ever watched Austin's The Science video series on Game Theorist and CharlieCast, he basically applies real-life science to video games and complains about how unrealistic they are, which is exactly what I'm doing in this video. Though I normally do Minecraft stuff, I sometimes do nerdy shit like this, or sometimes I do both in the same video. And if you like it, well, the subscribe button is right there. Please, I'm getting desperate. Well, have a good day or night, and see you next upload in like 3 months or something.